I've just joined MIT, so I was at UC Irvine before, I finished my PhD, and so I'm at this MIT University of Maryland thing because together a lot of people in Julia are working at these universities building these kinds of core libraries. So I'm going to tell you a bit about Julia because it's a kind of a newer language. Not as many people know about it, and I'm going to really introduce it to you through the perspective of DifferentialEquations.jl because I know that a lot of people here are differential equation modelers. And so I think a nice way to be able to show what the language is capable of is to show what it's capable of through differential equations. In a nutshell, this is the slide that a lot of people start Julia with. And the way that usually people talk about Julia is you say Julia is like MATLAB, Python, or R, but it solves the speed problem, right? So it's a little bit hard to see on here, but if you look on the edge here, there's C, and this is 1, and so this is the relative performance to C. So if a dot is higher, then that means it took longer, and this is in log scale. And what you're supposed to take out of this graph is that Julia, when you use on all these different types of test problems, Julia is able to get very close to C's speed, usually within 2x of C, sometimes a little bit faster, sometimes a little bit slower, but usually very close to C's actual speed. But the nice thing about this is that these tests are not just tests of just real world problems where you try to solve this as fast as possible. What this is actually doing is these tests are testing different ways that you can program in the language. One of these tests is testing how fast recursion is. The other one is how fast looping is. And so this really means that, in C, they've optimized all these to be as good as possible. But in these other languages, sometimes you're told like, oh, in R, you want to make sure you vectorize, right? Don't write loops, don't write recursion. But that can be kind of restrictive in the way that you're programming. And by solving the speed problem, what you're able to do is you're able to make writing programs easier because you can choose whatever style works for you, write it in this one high-level language, and in the end get code which is fast enough to be usable for your research. So one nice thing that Julia has is language operability. So here I say using pycall, which you can probably think, oh, that's going to call Python. You're using rcall and using a MATLAB package. And what I do is I say, let's import the interpolate function from SciPy. Oh, I should probably do this in the center screen. And here, let's get a titanium data set from MATLAB. Let's interpolate it using the Python function, and let's plot it using the plotting functionality from R. Right? So I use data from MATLAB, interpolators from Python, and plot it in R. And I do this all from Julia, and the output comes out. So if people have packages in all sorts of different languages, Julia is a great way to be able to just plug them together. And you basically say, hey, this string is just going to be MATLAB code. This string is going to be R code. And you just slice them all together in one language. So the syntax is very familiar. So the way I like to introduce this is that there's this paper by Desmond Hayem on Introduction to Simulating Stochastic Differential Equation Models. So if you look in SciAm Review, this is one of the top papers of the SciAm Review. And he gives you this really nice MATLAB code. And now if you take this MATLAB code and you say, well, let's change this curly brackets to square brackets. And I think that was about the only thing that I think there was one other change you had to do there. But yeah. For some reason, it doesn't like loading up this next slide, so it'll take a second. Oh yeah, so you also get rid of these ats because you don't need to put ats for your anonymous functions. That's a MATLAB thing. But when you do those few changes, you get almost the same looking code, but it just runs. So Julia, as a language, didn't try to be brand new in a lot of the ways it did syntax. It's pulled a lot of its syntax from MATLAB, from Python, from R. So it's actually very close to these languages, and switching over to Julia really isn't so difficult. You can take one piece of code and in less than a minute translate it over. For this example, though, we got a 10 times speed up over the original MATLAB code just by changing these brackets like this. So Julia's syntax is quite concise and mathematical. I like to show So there's this really nice this really nice cheat sheet put on by these quant econ people. So this is actually from economics people. Sorry, this is bringing the wrong people in. But even though there are a lot of one of the nice things about Julia is if you look through this whole chart, you'll see that Julia ends up being very concise with the way that it's doing things. There's a lot of, for in Python, you have a lot of these np.1s of a tuple of da-da-da, whereas, Julia pulls from MATLAB when it should be pulling, when it's more concise, and Julia pulls from Python when it ends up being the more concise one. And so Julia ends up just being a very nice language for a lot of these mathematical tools because, it had the hindsight of looking at the other languages and going, okay, these ones did well here, these ones did well here, and let's put this together to get the, try to get the best of both worlds. So I'm saying a lot of very good things about Julia, so let me give one slide where you say, okay, not everything is always going to be perfect, right? Everything has engineering and design trade-offs. What did Julia do in order to be a fast, high-level, concise language, right? There's no free lunch, so what trade-off did it need to make? One of the things that it does is that your type structures cannot be changed after they're created. So this is actually a lot of times in R and Python, you'll actually be taught in class to not do this. But if you have a Python object and you want to add a field to it, 15 lines later, if you want to add a field to someone else's object in a different package, R and Python allow you to do that. R and Python allow you to do pretty much anything. You can change a lot of the way that CPython is reading your code through its own debugger if you wanted to on the fly. But the fact that it's so dynamic like that makes it hard to optimize. So basically what Julia has done is said, well, a lot of best practices say you shouldn't make these kinds of changes. And it kind of leads to bad code, but also leads to unoptimizable code. So we're going to pull those out of the language and not make those things possible. That has some good things, that has some bad things depending on who you are. So all of the functions in Julia are JIT compiled via LLVM, which means that when the first time that the function is ran, it can take a little bit longer than the next time. So what that means, though, is that it's optimized for making your for loops, hundreds of thousand times faster. But if you're going to run something once, then it might have, like a 0.5 to 1 second delay the first time you run it. That's a trade-off. But if what you're usually caring about is the speed of very long functions, then that is what the trade-off that you're willing to make for those kinds of cases. All the functions specialize on the types of arguments. I'll get into what that is like. So Julia is interactive. So this is one of the interesting parts of the trade-off, right? A lot of people here want to always use an interactive language. But that itself is a trade-off because then it's harder to give someone a binary, right? A lot of the low-level software that you're using, they utilize a lot of C or Fortran code underneath because you can compile it once and you can add it to all these different libraries. So Julia chose to be on this interactive level like R and Python instead of being low-level like C and Fortran because that makes it more easy for users like modelers to be able to pick it up. But that does have a trade-off that means it's much more difficult to give someone a shipped binary program that hides all the code in the background. Let's see. There's a few more trade-offs, and one of the ones that I'll mention here is that so Julia has a lot of tools for code generation and metaprogramming, which, as you saw in the last talk, there's some really nice things that you can do. You can create all sorts of domain-specific languages, but that does mean that some code will be more difficult than other code because Julia is really a language that has a rabbit hole. You can use Julia like it's Python or R and just use array-based programming with to solve some basic equations, or you can go all the way down to build your own compilers within Julia, and you can, it's a deep language which you can keep exploring, and people still don't know how deep it goes, which could be a good thing if you want to go really far, and sometimes you don't want to see all that. So there are some engineering trade-offs that Julia has made, but to me, Julia is one of these emerging languages for scientific computing because this mixture of having concise syntax and speed in an interactive language really can be helpful for if you're starting to build models which are computationally, or which are limited by the computational power that you have. So how does Julia get a lot of its speed? And a lot of this comes from generic programming. So the way I'd like to introduce this is that object-oriented programming is centered around building representations of data and telling what those representations do. So you write out that this is my object. And now what I do to my object is I have these methods modify my object. But Julia takes a different approach to it. You say, this is my mathematical algorithm, right? You can say, my mathematical algorithm exists and is true exactly how you would run it on a computer is kind of irrelevant. And then someone says, here's my number type. My number type is a 64-bit number, and it knows what plus means and what multiply means. And when I put my number type into your algorithm, it generates a code, and that code is what's then actually ran on your computer. Now, the nice aspect about that is that a generic algorithm can have a lot of different number types and a lot of different array types and things put into it. If you have your generic code that says, this is this is an ODE solver, and someone puts in a new number type that has, maybe quaternion numbers or something crazy, right? Then, as long as you just tell that code how to do its multiplication and addition, now you have an ODE solver that works on the quaternion numbers. And so you get a lot of nice free features, which I'll explore a little in the rest of the talk from this. But that's also how Julia is getting its speed. Because what it does is it says, I have one generic function, but if you put integers into there, I'll generate one type of code. If you put floating point numbers in there, I'll generate another type of code. If you know how to read the LLVM IR, but basically all that's happened here is that it's generated one code that says, yes, this function, all it does is it goes to the spot of your processor that adds integers. And this code, all it does is it goes to the spot of your processor that adds floating point numbers. So if you're to create C code and compile it down, you get pretty much the same IR. If you compile this down with Clang, you get the same type of compiled code out. But what this is really doing in the background is it says, depending on what number types you give me, I will go all the way down and I'll try to optimize this as much as possible, even though at the top, it doesn't look like this all depends on types. This is just x plus y. Right? So it's not like Python and R in actual implementation. It's actually acting a lot differently under the hood, and that's how it's getting speed. But there's a lot that's going on that this generic programming, the way that it's compiling, is something we could tie into in order to get a lot of new features. So let's start talking about how this actually affects the users through the differential equation library. So the differential equation library is DifferentialEquations.jl, and it's able to solve ordinary differential equations, delayed differential equations, differential algebraic equations, stochastic differential equations. Basically, if you run the gambit of differential equations, this is what the library is for. And you can even mix it with discrete stochastic equations, so you can have part Gillespie, part ODE models, and run them all together. And so let's look through it through the eyes of the Rackauckas, because a lot of times in an epidemic model, you might have here's your population with your cyclic, and you add something to it. So the Rackauckas model is a nice one because I can add emojis to it later. Here's using differential equations. So you load up the library, and then you say, here's my function, which the derivative will go into the du part. The values are from the u. The parameters are from p. And so I say, this is the derivative of the first term, the derivative of the second term. I create a ODE problem, and I solve this ODE problem, and I plot the solution. So, if you've used another differential equation solver library before, this syntax will look quite familiar. It's just the Julia version of that. But you can also add a lot of DSLs and metaprogramming for syntactic sugar. So now let's use the DSL defined by something known as a macro. Right? So what we can do in Julia is if we have one of these @ symbols, the symbol after that, we can actually write our own sublanguage. And so there's a sublanguage for differential equations, which is this ODE def, where you just say dx equals here, dy equals here, and it builds the function from the previous slide for you. So you don't have to remember all the numbers for what values all your parameters are. It knows how to stick these parameters in the right order. And it's even compatible with Unicode. So one thing that you could see here is I use alpha and beta freely, but you can also use emojis, right? So this is now a model of D mice and D cat. And if you want to, you can use any, almost any Unicode symbol that you want. But we also have different DSLs where here is actually an SIR model where it says, you take a susceptible plus an infected, you get 2 infected. With a rate C1, and you take an infected, and it goes to recovered with a rate C2, and it builds the ODE systems for you. It actually also will build a stochastic differential equation for you if you ask for the stochastic one. So there's a lot of these nice DSLs where it abstracts you away from the function writing to the modeling level. So that way you can, when you're one away from the function level, this can help you make sure your model's correct, and we can make sure that your correct model then compiles down to something fast and give you, nice, good, accurate, fast solutions. So let's talk about some things that we can do that are very special with Julia. We can get more optimizations through our generic algorithms. So if you've ever heard of something called static vectors, these are vectors which are not actually heap allocated. They're not your normal vector. And what the compiler can do is that it can actually know the exact size of your differential equation and use that to compile a specialized version for exactly your input. What the compiler will do in this case is go, oh, I know this is the differential equation you wanted to write. It's of size 2 and all this other information. And it will compile a very special form so that way this exact ODE solver is very fast on your equation. So if you want to do something like a parameter estimation where you have to solve the same small model thousands and thousands of times, you can do these kinds of optimizations through the type level, where all I've really done is I said the input is a static vector, and then internally that turns everything in the ODE solver into using static vectors. Then that will optimize it for small ODEs. And what does that actually look like? So the first problem, which uses arrays, it has a time of about 65 microseconds. But then when I say I want to use static arrays, you can actually chop this down a bit. So you actually, in the median time, you chop down about 40 microseconds. So that's nice, right? There's a lot of different tricks like this. So I'm not going to show some of the other ones. You can turn the ODE solver to be something that works on the GPU if your equations are large enough. You can turn it into something that works distributed across multiple computers just by changing the input array type that you give it. So one of the nice things is that this DifferentialEquations.jl has now become a test bed for people, like especially me, to be able to implement the newest methods from the literature and be able to give this to users. And so what we actually do is we have this whole library when you can see that there's hundreds and hundreds of methods. Last time we counted, we were over 200. I think by now we're over 300 methods. And the nice thing is that if you really want to sit down and go, okay, let's find the most optimal method for this problem, so that way I can make sure I cut down my computational time. If it exists in the literature, it probably exists in this Julia package. So a lot of you might think that Julia is a younger language, so it's not as mature yet. But there's actually a lot of Julia packages like this one, which is very mature in the mathematics that it has actually implemented. So there's another Julia guy who just walked in. And we actually post all of our benchmarks online as well. So if you ever wanted to browse around and say, I have this difficult problem, we have, for example, you can take a look and see, does your problem match the form of this pollution model? So this pollution model is actually very similar to a lot of epidemics models because it runs on the same mass action laws with a bit of nonlinearities. And we have then further down, we have what the speed and the accuracy of a bunch of different solvers on each of these problems. So in some case, and so it basically says on this type of problem, this integrator can be, sometimes it'll even be like 10 times faster than other integrators. So it's nice to have the choice if you're trying to do these large models or large parameter estimation problems. Oops. So here's an example where I'm using the same problem as before, which had a median time of about, so remember, so it started out with the normal way you'd solve it. It was at about 120 microseconds. Then we can get it down to 80 microseconds or 88 microseconds by using static arrays. And then by choosing a new method, this ver9 method, we're now down to about 50 microseconds. So now we've cut the amount of time about in half from the DifferentialEquations.jl default. But I just want to point out, too, that this LSODA method, this is the standard method that you'd have from R and Python. And this is actually calling into Simon's C++ rewrite of this library. And in this case, that method ends up being 233 microseconds, right? So this is why, this won't happen on every single problem. On some problems, LSODA will be the fastest. On other problems, it's not as fast. But it's nice to have one library such that you can be switching around between all these different packages, all these different solvers. We're just using the same ODE code and calling into all these different libraries. And so if you really needed to optimize what you're doing, this is a nice library to use. Yeah.
So for those time benchmarks, are they to the same error standard?
Yeah. So in the benchmark library, it goes a lot more rigorously because I can show you in the DiffyQ benchmarks, it has the error and the timing of every single run, and so you can see like, oh, if a curve is lower, then the curve must have a faster time to hit the same error. So that's a much more rigorous way than what I showed up here, but yeah, if you want to go into more detail, you can look at that repo. But there's some other things that we get out of generic algorithms too. So a lot of times your parameters might have uncertainty, right? You have real data and someone says, oh, what is the death rate associated with this? And they don't say, oh, we know it's exactly 0.25. They say it's 0.25 plus or minus some value. So here we can say our inputs, we know exactly our initial condition, but our parameters have, this parameter has some uncertainty. It's 1.0 plus or minus 0.1. This one is 3.0 plus or minus 0.2. And we can put these numbers with uncertainty, and the output of our ODE is actually all numbers with uncertainties associated with them. And so you can generate solutions with uncertainties. And the nice thing about this is that we didn't have to sample, right? We didn't have to sample a lot of input parameters. We just solved the equation once with these number types, and it gives out the uncertainties. And if you were to actually have an analytical solution to your model, you'll see that actually this propagates the uncertainties exactly using something known as a linear uncertain propagation theory. So it matches the normal distribution and it matches the correlations between these normal distributions at least to the second moment or something like that. You can also use the generic algorithms to calculate sensitivities. So I won't go into too much detail of this, but if you have these things called dual numbers, so if you have a number with a derivative associated with it, then you can put these numbers plus derivatives through the ODE solver, and it will tell you So this output, what it's calculating is how will the x value, so how will the number of mice change if you were to change the parameter a at any point in time. So a small change in the parameter a will cause a large change in the amount of mice at specific time points of the simulation. Whereas in other points of the simulation, it will cause almost no change in the output. And so you can, so these derivatives are used in the backend in parameter estimation because those are the derivatives of the gradient to get the optimal parameters. But also this is a way to tell you how sensitive your model is to your input parameters. Because if you run this on a bunch of different parameters and plot them out, you'll see that sometimes the derivatives are almost zero, which means you can change those parameters around and nothing will change. And sometimes the derivatives are very large, and that tells you that your model is very sensitive to a few parameters. So being able to get sensitivities out is one nice way to be able to have another element of analysis in your model. So generic algorithms also give you arbitrary precision. So if you say, I really need a very accurate solution. So give me this solution using a 9th order method, right? So if you know about your ODE solvers, a lot of times like ODE 4.5, that's like a 5th order method. The order of the method is exponential in how accurate you're going to get. So here we say, let's get a 9th order method. That's something special in Julia. Let's get it to absolute tolerance of 25 digits correctly and a relative tolerance of 25 digits correctly. And let's use a big float number. And then here's a number, and our ODE solution is about 25 digits correct. I don't know if you need this in epidemiology, but at least it's pretty cool. So I know that some people are using it on more chaotic models, because chaotic models diverge exponentially fast. This is one way to be able to get a solution which is accurate enough to be able to avoid the problems of chaos for a given amount of time. Another nice thing is that you can add units. Yeah.
So I have another generic methods question. So I think, for example, RK, you can basically say, I want RK NM, right? And then there's an algorithmic way to generate the equivalent Runge-Kutta order. Do you have something like that?
Not necessarily, because you can always generate. So you can generate Runge-Kutta methods of arbitrary order, but that doesn't mean that they're necessarily good. And you have to establish a metric by what you mean by good. But good usually means for a given time step what the error will be on average across the set of possible ODEs. So order just tells you what happens as dt goes to 0. We don't use dt equal to 0, right? So if dt is kind of large, you can analyze how well a method will do if dt is non-zero. And so this ninth order method is a ninth order Runge-Kutta method due to Werner with optimized coefficients and optimized in a certain way.
For some particular setting. All right, so maybe ignore the specifics of my question, but there are several numerical solvers where you can give them things like, I need this order of precision baked into the solver, not just, hey, I want to calculate on really big numbers. Do you support the generic?
Yeah. So do we have variable order solvers and those kinds of things? Yeah, we do. So I'm just showing a few methods here, but in the list of 200, there's like an Adams method, which is a variable order between 1 to 12. The default method so if you actually don't give it a method, it will choose one automatically, and usually what it'll do is it'll choose one which switches between a method for non-stiff equations and one for stiff equations. And those can be matching order, different order, depending on tolerances you give it. So there's a lot of other things in the back end. But I mean, yeah, that's just one method, right? So I'm not going to discuss that in detail, but this architecture for DiffEq is something that we call a confederated API. And so you can just add your own algorithm type, and then it will send the problem over to your code, and you can tell it how to use that algorithm. So, so there's many different packages in the Julia ecosystem which implement algorithms for this API. And so some of them do adaptive order, some of them don't, and there's various reasons why to do it and not to do it. Yeah. But yeah, another nice thing is generic algorithms can have units. So the interesting thing about every single units example is that every time that I've gotten an example from someone, they're like, hey, we want to use units on this. The example has actually had incorrect units. So here's a quick one that I came up with that accidentally had incorrect units. I said, let's add units to our ODE model where our initial condition has the values in terms of kilograms. Right? So you can say we have kilograms of mice and kilograms of cats because we put them in a blender and we mushed them up and we're just seeing how much mass there is, right? And so the parameters, in order to make our differential equations be rate equations, our parameters must be per second, right? But it says that, oh, no, our units don't line up. Does anyone know what just happened in that equation? Well, what happened is that you do have these nonlinearities in the Lacour-Volterra model. So here you have kilograms times kilograms. So this parameter beta needs to be also divided by kilograms. And this parameter delta also needs to be divided by kilograms. And so every single time I try to come up with a unit example, I actually write down the units wrong. Every single time. So it's really nice to have this unit checking as part of the ODE solver because it can tell you whether your parameters are correct. And here it actually says that our solution is now in terms of seconds, and this printout for units is kind of long, but we have seconds, and then the two values of the solution at the 10th time point is in terms of kilograms. So what are some other features of DifferentialEquations.jl, right? So that walkthrough, these are some nice things that you get for free as being, I developed this in Julia, and so those are all the nice features that other people have actually came in to tell me that these features worked, and I was like, cool, that's really awesome. It's kind of cool that you can write a software that has more features than you ever planned for it to have, and then it takes a life of its own. But what are some other features that were intentional in this? The solution is continuous by default. So if you take that solution object, so it acts as an array which has time points and values that the ODE solver was at. But it also is a continuous solution. So if you say, what is the solution at 5.5 seconds, it says this is the solution at that time point. So instead of just having these discrete values that come out, you have a full continuous solution, and you can access it at any point in time. You can calculate maximums and minimums using the true maximums and minimums out of this. And a lot of these interpolants are order matching to the order that the differential equation was solved at. Another nice thing is that if you ever want to be like, what happens when you add noise? Well, you can say, you take your ODE and you add a second equation, which is the noise equation. So if you know your differential equation, you have the deterministic part and your noise part. And you say, now I have an SDE problem with the same ODE, but let's add this, this multiplicative noise to it. And out you get a Rackauckas model with multiplicative noise. And so this has a adaptive time-stepping stochastic differential equation solver in it. So that way it acts a lot like the ODE solver, but you just said add noise to it, and it's just as automatic as the ODEs. And you can even do delay differential equations. So for example, so here we say that instead of using cats and mice, now you have cats and mice. And this one value right here, we're going to use the value of mice from 1 second ago, or from 1 hour ago, t minus 1. And what you'll notice is that the cyclic behavior of the Rackauckas equations actually goes away when you add this delay to the model, which means that this is actually a very interesting feature that I found while writing these slides. And it's that there's some extra, if you do have delays in the way that your population is working, you don't necessarily still have the cyclic nature of that model they had. So if in the real world, the Rackauckas model might have actually been a very bad approximation. So that's some nice things that you get just by, it's very easy to switch between these types of equations, so why not do it? And you learn something about the models. So it's usable from R, Python, and the web. If you want to give this a try, there are these packages like DifferentialEquations.jl, which is registered into CRAN. Or let me pull up one of the vignettes here, where what this is doing is the ODE solver that this is calling in the background when you write this R code is our DifferentialEquations.jl. The nice thing is that means that you can use all 200 plus of our methods. You can use our SDE solvers, DAE solvers directly from R. So one of the things that we're doing as the Julia community is, since we are building a lot of these numerical packages, one of the next steps for us is to expand our audience to not just be people who are Julia users, but also R and Python users. And we also have tools that can be used from the web. I just like showing this one because it's cool. And so here's the Rackauckas on the web. The server timed out though. Usually it's on the web. It needs to wake up the solver. I'll hold on to that for a bit. And one of the things that, now that Mike's here, I might actually want to talk to him about this. We're in the near future, what we're trying to do is trying to get other DifferentialEquations.jl models to compile such that you can build nice little slider outputs and stuff to be able to use from web browsers. Kind of like what you saw in the previous ones, but we want to be able to use this full stack that has also these stochastic differential equation tools and delay tools and continuous outputs and all that. So DifferentialEquations.jl has a large active developer base. So we do have, I think right now we're counting 40 contributors. But you're lucky because you have I'm the guy who started it all. So if you do want to give Julia a try and you want to give differential equations a try, this is a good workshop. And you can bug me all you want to be able to learn how to use this. So if you have any questions, just let me know.
Is there a good debugger for Julia?
Is AST interpreter 2 in Juno yet?
Yes, you can grab Juno, the IDE for Julia, download Julia Pro maybe from the website, and you can grab AST interpreter. Well, there's a debugger built into that. Basically, there are instructions around somewhere, so that works really nicely.
Yep. Yeah, so Julia is kind of newer, but these tools are very much hitting their prime time. So as Simon said, our 1.0 release was just 1 or 2 months ago, and so we are just barely gotten to stable. Yeah.
Could you say a little bit more about that uncertainty analysis?
What about it?
So what are the assumptions in it? Like so no sampling. I'm guessing you just evaluate it at each of the edges.
Yeah, so what it does is something called linear propagation theory. So linear error propagation theory, it means that every 2 operations between things will propagate the right normal distribution. So you say that my parameters are normal distributions, and then when you normal distribution plus a constant, well, a constant is just a normal distribution with 0 variance, what should that output be? The next thing that also does is it keeps the partial derivatives between each of the variables. So that way, if you have normal distribution divided by normal distribution, but they are actually dependent, right? You know, x divided by x should be a constant, the constant 1, right? So it is linear error propagation theory plus the ability to track the dependencies and correlations. So it is some kind of propagation of normal distributions to second order. It does chop everything off at second order, and there are some other research projects that we're doing to be able to try and encode full probability distributions into numbers, but that's further down the line. For now, you got, you know, for now you get moments and variances, which is for a lot of people enough. Yep.
I've seen some work done recently on ODE integrators run on GPUs with quite significant speed improvements. Is this something you're looking at or planning to look at?
Yeah, we're looking at it quite a bit. There's two different regimes that you have to think about when you're dealing with this. One regime is the very large systems. And we had so I run this blog, Stochastic Lifestyle, and on this blog we do have one blog post which shows how to use our ODE solvers on the GPU. And it really just is about using these generic algorithms where what you're able to do is you say that these arrays are arrays that are on the GPU, and it'll take all of the internal arrays of the solver, put them all on the GPU, and all of the internal operations of the Runge-Kutta methods then compile to be kernels on the GPU as well, so the whole thing actually runs on the GPU. That's quite nice. There's still a lot of improvements that we need to do with it in order to make it work with all the stiff solvers, because we need to make sure that the factorizations automatically go to the GPU. And but we're getting quite there. So privately, I'm talking with some people about how to finish these last few steps. I think I'm aiming to get that done around January, February. But that's for large models. On the complete other end, when you have a small model, small ODEs are algorithms which are very serial. So that you have to fix that by either two ways. You either have to say, well, what's important to me is to solve the same ODE with different parameters thousands of times at a time. In order to do that, what you need to do is you need to compile the whole ODE solver to the GPU. And that sounds crazy, but there is this thing called CUDA-native.jl, which is almost able to, so what it does is it takes a Julia code and it compiles it to the GPU. And now you ask the question of, can you just take someone else's package and compile that all as one GPU kernel? You can under some constraints, but we need to work around those constraints to be able to get the ODE solvers working on that. But we do have some ways that we know how to do that. So there's some fancy thing in the background which is called cassette.jl. If you've ever heard some Julia talks, this is some fancy like dynamic compiler tools. And what we really need to do is we need to swap out our heap allocated arrays to GPU arrays and things like that in order to make this work. But yeah, there's an idea for how to get the whole ODE solver compiling to the GPU, and this is one of the things that we're having one of our students work on actually. So big systems is that, really small systems there's this. There's actually a third way where you can say, let's throw out all of the previous ODE methods and let's use a method which is parallel in time. Parallel in time might not make sense, but there is a way to be able to multi-grid time for your solution, and then you get a large matrix equation, and solving this matrix of factorization is then equivalent to solving the ODE, and that's a third method, and there are some people implementing those into Julia that we're talking with. So yeah, we're really aiming for the GPU tools. This guy is one of the people who was part of this whole making sure these CUDA arrays work really well. And for a while, they required a source build of Julia. Now with Julia 1.0, anyone can use these CUDA arrays with CUDA native and compile a lot of Julia codes directly to GPUs. And so now we're exploring how to make this work with whole packages and do all this cool stuff. Yeah.
Thank you very much, Chris.
Yep.